Conservation of mechanical energy. We can simplify the visual and imagine a pendulum instead of the girl. At the point where the pendulum, bob, is closest to the ground, the height, h, would be the smallest. Hence the gravitational potential energy, EP, at this point would also be the lowest, with the ground taken as the reference point. At the lowest point of the bob, the magnitude of the velocity v of the bob is at its maximum. Hence the kinetic energy Ek of the bob is at its maximum. As the bob swings up, the bob reduces in speed and gains height. The kinetic energy reduces, while the gravitational potential energy increases. When the bob reaches its highest point above the ground, the gravitational potential energy Ep is at its maximum, whereas the kinetic energy reduces to zero. The bob is stationary for an instant of time. As the bob swings back, its kinetic energy increases from zero, while its gravitational potential energy reduces until it reaches the lowest point. Here, the kinetic energy is again at its maximum, and the gravitational potential energy is at its lowest. When the bob moves to the other side, the kinetic energy of the bob again gets converted to gravitational potential energy. We can see how energy is converted constantly from one form to another. The bob continues to swing and reaches the same height after each swing. We can now state the law of conversion of mechanical energy. In the example of the bob, if there is no air friction, that is, the resistance offered by air molecules to the motion of the bob would continue to swing forever. Hence, we are ignoring the presence of air friction when we consider the conservation of mechanical energy. The law of conservation of mechanical energy can be written as Ek1 plus Ep1 equals Ek2 plus Ep2, where 1 and 2 are different positions in a gravitational field. Since the total mechanical energy is conserved, the position of the object becomes irrelevant while calculating mechanical energy.
Starting to feel it? Now go master it with Maskitv.